The next thing we need to talk about here isn't exactly a type of energy, but it's very, very closely related to energy, and that is work. So when a force is exerted on an object, imagine pushing or pulling an object, it can add or take away energy from that object. And work is the change in energy that results from a force being exerted on an object over some distance. There are a lot of examples of this. We can think about frictional forces being exerted on an object as it slides across the floor, taking away the kinetic energy of the object as it slides to a stop. Okay, we can think about someone going to the gym and lifting weights and exerting a force on those weights as they lift them up over their head, causing them to gain potential energy. We can think about a person just throwing a ball, right? The ball starts from rest, you exert a force on it as you throw it, and you give that ball kinetic energy. So work is the change in energy of an object that results from a force being exerted over some distance. Okay, so like I said, it's not exactly an energy, but it does represent the change in the energy of an object when we exert a force on an object over a distance. And we refer to this as the work-energy theorem, this link between the energy, the change in energy of an object, and the force exerted on it. And we're going to look at this mathematically in a second, but conceptually this is a really, really important idea that forces exerted on objects do work on those objects and change the energy of those objects. So mathematically we have two ways of finding work. The first is F delta x cosine theta. Okay, and so this allows us to calculate the work from a force and the distance over which that force is exerted. Okay, we'll talk about this theta piece in a second, but that angle is the angle between the force and the displacement. Okay, and we'll look at some cases for that on the next slide. The other way we can find the work, and this just goes back to the definition of what work is. Work is the change in energy that results from this force. So we can just say that work is delta E. In both cases, the work is going to be in terms of joules. Okay, it is a change in energy, so it's going to be measured in joules. So let's return to think about that theta there that we just introduced on the last slide, and that F delta x cosine theta equation. And let's think about the possible cases for theta. So one possible case is that the force and the displacement are in the exact same direction. We're pulling an object to the right as it slides to the right. In that case, our angle between this force and this displacement would be 0. Thinking back to our equation, work equals F delta x cosine theta, all right, cosine of 0 we know is going to just be equal to 1. And so that means that that equation simplifies to work equals force times displacement. Moving down to this situation here where we have a vertical upwards force as the object is sliding to the right. In that situation, the angle between our force and our displacement would be 90 degrees. And if we remember our unit circle, we know that cosine of 90 is just 0. And so that means that our work done in this situation is going to be 0 joules. All right? A force that would exemplify this would be the normal force, right? That would be a force that we often have that's going vertically as an object is sliding horizontally along a surface. And if we think about the normal force for a second, and what work really means, the change in energy from a force, as an object is sliding horizontally across a surface, that vertical normal force isn't adding to its energy, it's not taking away from its energy, it's just there. It's just supporting the object, but it's not changing its energy. So it makes sense that the work done by that force would be 0. Moving on to the bottom right here, we have a situation where our displacement's still going to the right, but our force is back to the left. Okay, the angle between this and this would be 180 degrees, all right? And we remember that cosine of 180 is just -1. So once again, if we think about our equation up here, that simplifies to work is just force times displacement, but it's negative. If we think about a force that often would do this, friction would be a great example. Friction is usually opposing the direction an object is moving, okay, if we're talking about kinetic friction and it's sliding. So this would be a good example here. And if we think about the meaning of work, once again, it makes sense that our work done would be negative because friction is going to take energy away from this object. So the work done should be negative, showing that it's losing energy because of that frictional force. And then the last example is just anything in between, some other theta between 0 and 180 but not 90. okay? And there we're just going to use our full work equals F delta X cosine theta equation. Now, why do I point this out? This isn't something to memorize. You shouldn't know off the top of your head all four of these cases. This equation will always work. As long as you correctly figure out what that angle is, that equation will always work. But I think it's a useful exercise to think about the possibilities for work. All right, conceptually with work, three really important things that you will see, and they all really come back to this equation, work equals F delta X cosine theta, but they're useful to point out because they will come up in conceptual questions frequently. In order for work to be done, we first of all have to have a force. That's a given. Work is the change in energy that results from a force, so obviously we need to have a force. Second, there has to be a displacement, okay? We have to actually make the object move. So this situation here, with our prisoner trying to escape, he can push on that wall all he wants with all of his might all day, but he'll never actually do any work because he's not actually going to make the wall move, all right? Until we make an object move, no work is done on it. We don't transfer any energy to that object. And lastly, the force and the displacement cannot be perpendicular. Unless all three of those conditions are met, the work done is going to be zero. And so that's an important thing to keep in mind, especially when we're doing some of these conceptual questions. All right, so let's go ahead and do a practice problem here. So we have a 15 kilogram block here that's being pulled horizontally a distance or displacement of 4.5 meters to the right. And we have the list of forces here that are acting on the object during this time. And what we want to do is we want to calculate the work done by each force. So I'm going to take these one at a time. I'll start with my pulling force here. So each time I'm doing F delta X cosine theta. So for my pulling force, the force is 120. My displacement is 4.5, and the theta is going to be the angle between the force, which is going like this, and the displacement, which is directly to the right. So that 30 degrees here is my angle between force and displacement. So I end up getting that the work done here is going to be 467.7 joules. You might be thinking, why didn't we need to break that into components? Two reasons. Number one, here's the beautiful thing about energy is not a vector, okay? So we don't really have to worry about X and Y energy. Energy is just energy. And when we're solving for work, that cosine of theta term here takes care of the angle, okay? So you can just put in the full force, the full displacement, and the angle between those two, and you don't have to worry about breaking things into X and Y components. The other thing that you can think about, though, is if we did break it into X and Y, this X component would be 120 cosine of 30, which is ultimately what we ended up doing here, 120 times cosine of 30. And that component, the X component, is the one that really does the work, okay? The Y component, which is the 120 sine of 30, is perpendicular to the displacement. So the work done by the Y component would just be zero, and all we'd be left with is that force from the X component. So if you did want to break it into components, you could do that, but you're doing more work than you need to. You can just leave it as F delta X cosine theta and use that full magnitude of the force and just account for the angle between your force and your displacement. Moving on to my next one, I'm going to go ahead and take a look at my normal force. Okay, and so the work done by my normal force is going to be F delta X cosine of theta. In this case, though, my angle is going to be 90 degrees, which means that my work done here is simply 0 joules. Okay. For the force of gravity, I'll do that force next. Same idea, but once again, my angle is 90 degrees. Okay, and the reason here, right, is the force of gravity goes straight down, the displacement is to the right, so the angle between down and right is 90 degrees. All right, and that means that the work done by gravity is also going to be 0 joules. Right. Both of these make sense, though. Since our object is traveling horizontally, these forces pushing up and down aren't going to add to the energy, nor are they going to take away from the energy. So it makes sense that the work done by both gravity and the normal force is 0. Lastly, we have the force of friction. Once again, work for that is F delta X cosine of theta. And so the work done by that frictional force is going to be my force here, which is 30 times my displacement, which is 4.5, times cosine of the angle. In this case, the angle is going to be 180 degrees. My displacement is that way, my force is that way, and the angle between right and left is 180 degrees. Okay, and so for this one, I get that the amount of work done by that frictional force is going to be negative 135 joules. Makes sense that it's negative because friction is going to take away energy from my object. For part B here, we want the overall change in energy of the object. Keep in mind that the change in energy is simply the work done on the object, so we're just going to add up all the work that's done on this object, the 467.7 plus negative 135. Obviously, the other two forces don't do any work, and so we end up getting a total work done here of 332.7 joules. We have a few more practice problems here. On the last slide, we did some where we were calculating the work done based off of the force exerted on an object. That's not the only way, though, that we can calculate the work done. We also can find work by thinking about the change in energy. Either equation will allow us to find the work, because work is the change in energy that results from a force. So in this case, an elevator car with a total mass of 2,000 kilograms lowers passengers from a height of 15 meters to a height of 3 meters. What I would be thinking about is what kind of energy is changing, and in this case, the kind of energy that's changing is going to be my gravitational potential energy. Anytime I see something about a height, I'm thinking about gravitational potential energy. So my work done is going to be my final gravitational potential energy minus my initial. Anytime I do a change, okay, it's always final minus initial. In this case, final energy minus initial energy. So it's going to be mgh final minus mgh initial. I can go ahead and plug in the things that I know here. And I end up finding that my work done is negative 235,200 joules. For part B, we have a person carrying a 10 kilogram box 5 meters. The arms exert an upward force on the box. We want to know how much work is done by the arms. Well, if my force is upwards and I'm carrying it horizontally, that's going to be my displacement here. That means that my work done here is 0 joules because the angle between force and displacement is 90 degrees. For part C, a biker speeds up from a speed of VI to a speed of VF on a flat surface, and we know the mass of the biker, so this is another case where we're thinking about our change in energy. In this case, we're moving, so we're thinking about kinetic energy, 1/2 mv squared. So our work done is going to be our final kinetic energy minus our initial kinetic energy. We can go ahead and substitute in what we know here, so our final is going to be 1/2 mass times V final squared. Our initial is going to be 1/2 mass times V initial squared. We could leave our answer like that, or we could simplify and factor out the 1/2 m, and then we're left with work is just 1/2 mass times Vf squared minus Vi squared.